Okay, sure. Yeah, I'm Tim Hall. I'm Business Development Manager at Engenuity. I guess I don't need to introduce Engenuity because we're going to do the whole thing now. And then, yeah, any questions you've got about the presentation, feel free to ask at the end. So to introduce Engenuity, we are a provider of advanced engineering services, and we've been involved in the composite industry since the 1990s. We sort of have three main strings to our bow, which I'll talk about in more detail throughout the presentation. So one is our in-house test and characterization lab, which we use a lot for generating material cards for analysis. We also have our own novel techniques that we've developed where we've seen the gap in predictive capability. And I'll talk about a couple of those, C-Zone and Firmware. And then the thing we're maybe best known for is our advanced analysis. So this is sort of all sorts of structural analysis in fatigue, crash and vibration and everything else, all the way through structural optimization and developing layout manuals for manufacture. We have a wide range of clients throughout the supply chain. So we work with, say, our materials characterization lab works a lot with the big names in material, composite material manufacture. And then we also work with a lot of component manufacturers, so they can take on more of the projects that they're working on. So we can do the engineering side of the projects and they can do the manufacture. And we also work with OEMs when they're looking at which material should they use for particular applications, or they need some help in the analysis side, either for advanced analysis or for sort of capacity. We're based, this isn't a particularly accurate map, but we're based down sort of between Gatwick Airport and Brighton, down in West Sussex. So we'll first just talk about our work on the material side and our Composite Test Lab. I mean, it's a pretty fully stocked lab with everything you would expect to see in it. A couple of instrons and our own drop tower of our own design, environmental chambers, and some other equipment. Lots of fixturing. We cover all the normal static stuff you would expect in terms of tension, compression, shear, flexural, fracture toughness. But also going into climatic conditioning. So when preparing samples, you can keep them in chemicals, or you can freeze them or heat them, and testing them in different environments as well. So our instrons can go inside an environmental chamber to do hot and cold testing. They can also do fatigue. They can do fatigue in the environmental chamber. Still a really common failure mode we see you can see in composites that often people don't characterize for. And then into things like adhesives and sandwich panels, so looking how those peel and shear, and we can characterize all that, including in different environments. And then one area we're probably the global leaders in is composite crush and dynamic testing. So that's the picture on the left there is our dynamic testing rig. It has a lot of mass in it. It also spring loaded. It could generate a lot of energy. And it's used to characterize the coupons in their dynamic behavior. And we also do sort of custom things. So we had a request recently for a more sustainable composite that was going to be used in an interior of a car. And they didn't want a high energy sort of crush characterization. They wanted a more low energy one. So we built them a specific rig for that, which is now available to our customers as well. And then the lab started as our way of generating good, reliable material data for our analysis team. Now, obviously, it's used by a lot more people to generate good, reliable material data. But we've brought in all the techniques that we thought would help us. So we mainly use DIC for optical strain recovery. That means we can look at the strain right through into the failure modes, so we can characterize further into the behavior of the material, into the failures. We do all our own coupon preparation, including these double dog bones you see on the right. You can see the speckle patterns there for the DIC. There's also QR codes on those. The lab runs its own, or our own, laboratory management system, so we can handle a lot of coupons very quickly. It's almost entirely paperless. We just scan in the coupon codes, and it tracks all the information, even back to where on the plaque the coupon was cut from, which has actually taught some manufacturers about some potential failures that they had missed. but we could pick out of our data that we'd generated on their materials. And then, so why do we do all of this? Well, there's a couple of key applications for all this data. One's material screening. It's mainly an OEM request that they have a few different materials they're picking for a particular application. And what we can do is take a quick look at each of those materials, but we can also link it to the analysis, so we can say for this particular application, so this example on the right, compressive strength was the most important property, and then there's some other important properties, or we can compare the materials and we can weight up which one would be the best. And in this case, material free, it was sort of consistent across the range, but not the best at anything apart from compressive strength, which was the most important, and overall came out on top. So in the composites world, you have so much choice of materials, fibres, resins, binders, cure cycles. It can all make a difference. So this can be a really useful exercise, and it's really important to do right at the beginning of a project, because the next area that we do is to look into is material characterization. So this is creating these material models in programs like Abacus and Dyna and Radios. So you have really accurate models of the materials and how they behave, not just sort of the linear properties that you normally get off a data sheet, but right into the non-linear and the failure properties. And again, a lot of this is automated. So all these sort of things down at the bottom here, the buckling calculation and things, these are programs we've written so that if we're doing this sort of work, a lot of the work we have to do that would normally be manual is just automated, and the computer calculates all the properties for us. And then we can start to do the correlation between the material model in the analysis code and how the material is behaving in our lab. This is one example of our material characterization. We chose one of the toughest properties that you would expect to see in a normal sort of linear material characterization thing. It's fracture toughness. It's a very difficult failure mode to characterize because it's so sensitive to the notch, and it's just the way the failure works. So these are some of the correlations we got on fracture toughness. And again, it's sort of two sides to it. It's about how you generate the data for the start off in the lab, and how you do the correlation in the analysis program as well. And we'll talk about, there'll be some at the end. We've got some applications where this sort of thing is so important to be able to use composites in a predictive way. So techniques, we use a lot of commercial software. We have a full suite of Altair, LS Dyna, use a lot of Abacus, Creo. But I'm just going to talk about some of the techniques we've developed that are sort of unique to Engenuity that you can license in some cases. So the one we're probably best known for is Composite Crush. C-Zone is our program. It's available as an add-on to Abacus through Simulia, and it's used quite widely in Formula One. And it's a purely predictive tool for composite crush analysis, and it's the only one we know about. We created this, and we created it because we searched on what everyone else was doing, and no other tools were purely predictive. This example on the right, you've got a deceleration trace and an energy absorption. We did all this testing with General Motors. That's their sled in the top left, and their trace from the experiment is in white. And every time we did a test, they insisted that we put forward our prediction first before the test, and that was our prediction in red. And we have a lot of these different angles of crushing and all sorts. And what C-Zone is doing is, I mean, FEA in general is not well suited to doing crush, because crush is such a continual process. And obviously in finite element modeling, you're breaking everything down into little sections, and C-Zone just sort of smooths that out and makes it a more continual crushing process. And it requires just an extra, the one main extra characterization property called crush stress, which we used the test rig we saw the drop tower earlier to measure. Plenty of applications of this, which I'll go into in the future. This also works just as well for sort of continuous fiber composites and for discontinuous fiber composites, because that crush stress property is sort of an average. So it works pretty well, very well for both types of composite. This example cone we used, we use it a lot, but the idea is that it has different layup changes, it has different changes in section, it has a metal insert. It's meant to have some complexity to it, to sort of So it's a standard cone, but it sort of copies some real life features that you would expect to see. So compared to the blue trace here, that's a, you know, Abacus, one of the probably the best structural program for composites, it's just absolutely nowhere near what's really going on in this situation. So the other tool, this is really in development, and it's aimed mainly at SMCs, and it's to allow them to be used for more structural application in these short fiber composites, particularly as we get into circularity and we start seeing more from sustainable composites and trying to use short fiber composites and what do we do with these materials. Our principle, which we think some of the other software developers have missed, is that you're going to have all of these. Every time you make one of these parts, it's going to be structurally unique. It's going to have a slightly different layout to the last one you made, and that's because you've got random fiber directions in there, and sometimes those random fiber directions will land in the critical structural points of your material, and they won't be as stiff as strong at the critical points. And so firmware has been developed for SMCs to be able to predict, to I guess give a range. It's a statistical problem. So you don't have one answer for how a part's going to behave. So it can show you your sort of weakest, strongest parts, your least stiff, your most stiff parts. And so this is the sort of results we would expect. Again, we're looking at one of these cone parts, but a typical, this is just holding it at the right end and pushing it on the left end. And we can see we get a range of different failure modes, a range of different failure loads. And you can start to see a bit sort of, you could statistically plot that. And this gives you a much better idea of what your safety factor is. But also looking at the bottom right, you have a number of different failure points. So this is what we call a cumulative failure plot. So this is all the plies that have broken during these failures of say, that's a population of 100 parts. And so sometimes you're failing in one corner and sometimes you're failing at a different place. And unless you sort of understand that each part can be structurally unique, and you just use a best guess of how it will work, a best guess will give you a best guess of where it will fail, but it won't give you a variety of different failure points. And the point of all of this is to guide the designer. Where can we remove material? Where can we add material? And we have one of the big SMC manufacturers has actually started using this program and find it quite useful, but it's still really in development. So moving on to our analysis side, this is going to have quite a few nice simulations of some of our crush work and some of our other projects, but we'll just start with a sort of general chat. I mean, we all know that in composites, the beauty of them is that we can really tailor what goes into those materials, you know, where the layups are, which orientations were strong and weak, and we can take out material where it's not required, and we can make much lighter components. One of the real strengths of Engenuity is that we have so much experience in so many different areas of structural optimization. So this is a part for a bicycle. We've worked on lots in the automotive world, from race cars, you know, Formula 1, Le Mans, through to mass market cars, into aerospace, medical, heavy industry, marine. So we've just worked on lots of different applications, and we've been doing it since the 1990s. And so if you need help in one of those applications, we could be a good guys to speak to. So I could talk about a few of the things we can do. One of them is ballistics, and people looking at it. When I first saw this, I thought, well, I'm probably not going to be trying to make a bulletproof thing out of composites. But this has become so important for battery boxes and looking at penetration of stones flicking up the road. And again, it's a time where your material properties and what you've characterized is so important to getting this simulation right, to knowing how many plies you need to stop that stone entering. And just something that would be a real pain to do via a prototyping route, much more expensive and much more time, and probably wouldn't give you as much information as you'd get from being able to simulate it accurately. Another area we're doing a lot of work on at the moment is hydrogen storage. There's going to be a lot of people saying a lot of composite material to make pressure vessels, and the engineering of them is quite tough. You know, you want to be competitive. The weight stored per weight of tank is a really important factor that customers will look at when deciding. And so getting that engineering right And it's sort of the perfect application for Engenuity because it starts right at the beginning with the material screening, which is the best material to use for this application. You're probably looking and going, right, tensile strength might be a really important factor here to handle the pressures. But the standards for these have lots of different, they have a penetration rating as well, really high burst pressure. And again, something that's really difficult to do through prototyping. So if you want to burst one of these at, say, 1600 bar, it's quite tough to find places that will do that. One step. Let's just get this animation playing. Yeah. So so we developed this wheel for a Chinese company, and this is one of the more challenging load cases. I just wanted to show. So this is sort of the most extreme load case, and the challenge was, like at this extreme load case, the wheel can't shatter. So you're looking right into the non-linear material properties, the failure properties of the composite that makes up the wheel, and also doing a non-linear explicit analysis to be able to work this out to see if it's going to happen or not. Again, something so expensive to do through prototyping and much better to do in analysis. So by characterizing the material right into the failure region, into the non-linear region, and accurately characterizing properties like fracture toughness, you can generate these simulations, and you can show that yes, the wheel's cracking. We thought it would at this extreme thing. You can see that everything's included in the model. You can see that the suspension's moving. You can see that the linear properties are there. The wheel's flexing. But it's a much bigger task to go into the failure properties and predict that it's going to crack, but it's not going to shatter, which would be a much worse result. So you've written off the wheel, but you've not written off everything else. I know a few people in the in the group will recognise this is the Toscar project for JLR. Engenuity worked to place on the structural simulation side. So we've got here, it's a thermoplastic overmolding with selective UD parts. So I think the body in white for this car was over 100 parts in aluminium, and we were looking to increase the torsional stiffness, and we replaced only one part in composite, and we got the whole torsional stiffness up by 7.5%. And so little of the expensive UD material, most of it's plastic, and that got it in at comparable cost as well. We've got a few C-zone applications now. This is a project with Nissan on the Nissan Leaf, looking at if the steel floor could be replaced by a carbon composite floor. And you can see a picture there of the part we're talking about. And normally in these mass market automotive projects, people say, well, yes, you can save a lot of weight, but it's much more expensive. You know, it's going to be 3, 4, 5 times more expensive to do it in composite. This part was about 40% more expensive. And you know, there were some clever things done again with the manufacturing. But talking to University of Cranfield, who we did the project with, they said that one of the things that really surprised them was how little material they needed to achieve the crush performance. So we did this side pole impact of the floor, and they said they never would have known that without using us and using C-zone to predict how far the side pole would penetrate in, because you're obviously protecting the batteries as well as the occupants from this one. This was for BMW. So BMW really wanted to see, they weren't saying, we're going to build a car out of composite, can you do the analysis? They wanted to take it all in-house, and they wanted to see if this software, as well as all the characterization techniques, could be used in the future to make more cars out of composites. So this was an existing chassis. They took out a lot of the metal parts and replaced them with composite parts, and they used C-zone, and we guided on the material characterization to do this prediction, and they wrote a whole paper about it. And basically, I think visually you'll agree they're nearly identical. Exactly what C-zone predicted would happen is happening in the crash test. Looking at the acceleration traces, were pretty much there. The paper goes on to explain that they actually had a failure in a metal riveted part. I can send people the paper if they want to, and that's sort of the initial composite parts are doing the initial energy absorption, and those acceleration traces are perfect. Then there's this failure in I think it was a riveted aluminium part that they weren't expecting, that then knocks things off a bit. Before I think the sled hits the wall or something and it just goes wrong. But you know, the levels are right. The initial composite crush part, which is the key part, the energy absorption part, is really doing what it should do and says what we said, what CZen said it would do. And this is from their paper, and you know, this paper, as I said, was about could this technique be used in the future so we can make more composite cars? And obviously it was lighter weight, but they concluded that CZen works as a predictive tool to simulate crushing behavior, that only a few additional material properties need to be measured. So that's this crush stress property, and that they could use this to use purely virtual driven development of CFRP crushing structures in the near future. A quote from them: "This new methodology, CZen, will form the basis for further development of CFRP body and white structures for passive safety applications within BMW." And this is the last sorry, the last application, and one of my favorite videos that we have. This is for sail GPs. These are the fastest race sailboats in the world. To give you a sense of scale, these boats are nearly 50 feet long. They're 15 meters, so they're big boats. Inside the hulls, you have, I think there's 5 crew. So there's actually people in that where that hull is penetrating the other hull. You have people in there, and they get very close when they're racing, and they go very fast. So this is obviously a big risk to crew safety. And this is the sort of baseline simulation of what would happen if they collide. And so we know through this is you know, through all the validation work that's been done on CZen, we know this is pretty realistic and could be pretty dangerous if it happened. And again, you can see all the other effects in the simulation as required. You can see that in the left-hand screen that the boat's actually sliding a bit as it gets hit because it's in water, and it's not it's not a rigid test. It's got that part of the simulation. We're also working on them with a project to look at hydrofoils. These are, you know, you can see those at the front of the hulls there. The hydrofoils are very thin bits supporting very heavy boats, and so structurally they're tough anyway, but they also have really important hydrodynamic properties. If they cavitate, so if they start to form bubbles underneath them, then the lift drops right off, and the nose of the boat plunges into the water. So if you can optimize the structures, which is what we're looking at, then you can make thinner parts and you can reduce that risk of cavitation. So I'll just do a quick summary, but it's really a summary of our process, and just to reinforce that a lot of people have some of these capabilities in-house, and really it's just a menu that people can pick and choose from. If you want material data but you want to do the analysis yourself, that's fine. That's absolutely fine, or any other bits you can mix and match as required. So our process is material, so it's selecting the best material, do accurate testing to recover the properties, and then characterize for simulations. Do this extra step of putting the material data into material models on ANSYS or Abacus or LS-DYNA, etc., so that you can do your simulations. Define accurate load cases. We haven't talked about it much, but it's so important to all of this work, and we help with that. And then through the analysis, use the best techniques, whether they're the sort of commercial tools that we can buy or the Engenuity tools, and use that to create efficient structures that are lightweight, strong, durable, cheap in some cases. You know, you can do all of this in analysis. You don't need to be doing prototyping or guessing or making it too safe or other things. You can accurately predict it now. And then we can do that all the way through to defining the layouts for manufacture. That's me. As my number and email address if anyone wants to get in touch. And we're also happy to have people come and visit and look around our lab and learn a bit more about what we're doing. And so there we are, we're in West Sussex. Thanks very much for listening. And I think we're moving on to questions.
That's great, thanks Tim. I'd definitely like to come down and have a look at the labs and see what you guys are doing down there. It was yeah, I learned an awful lot in that presentation, so thank you. Just checking, there's been a couple of messages come through on the chat. I think one of them's already been answered for you. So first message we've got, first question, sorry, is there any modelling or simulation on material resistance to thermal or fire available?
We really look at structural, so we haven't looked at that. I mean, we can do high temperature structural to a certain degree, but no, I expect that there is modelling and simulation out there for fire, but it's not something we cover.
Okay, next question in the chat box, then there's a couple of raised hands. So next question is the SMC analysis tool available as a plugin to Abacus like C-Zone?
It is available. It's a bit messier. That it uses Altair Hypermesh as the preprocessor, and then Abacus as the solver. So it is available. It's not available through Altair. Altair would direct you to us. We issue licenses for the SMC tool firmware. But you need both Hypermesh and Abacus solver to run it. Normally, most companies have at least one of those already.
Okay, we'll move on to Stephen Brooker, who has raised his hand, and then you've got a couple more questions coming on the chat.
Okay.
Hi, Tim. Yeah, no, it's just a background. It's interesting the stuff you do around SMC. So for us, we're using polyester-based SMC for essentially manhole covers, and predominantly to date, we're using, the problem where we sit in our industry is, you know, we're taking a conventional construction product and then you're earning into your aerospace and your automotive grades. So there's a price point to hit in performance where, you know, where we're paying maybe say £1,000 a ton roughly for SMC, then suddenly you can go into carbon, you're at say £20 a kilo. So for us, we've actually started looking at where we see the market's going is a bigger demand is for using bi-directional SMC, and we are currently like doing hybrid prototypes where we're actually mixing SMC. So in the bottom where we need in cover our high tensile regions, we are using high performance SMC, but to date we're actually at a roadblock at the minute because we know the strength of material we need in the material, but it's just trying to get that availability, which is the issue.
Okay.
So I don't know if it's something you can offer yourselves, like an advice or supply of, say, do you actually offer SMC builds or recipe formulations?
I mean, we possibly know the right people because we're sort of working with them. Maybe it's something to take away after the meeting. It's something I'd be pretty confident that we could simulate. I mean, we've definitely done that before using firmware, is doing sort of a hybrid material approach where you have two different materials to try and achieve one goal.
I think it's very good at what you showed on the SMC simulation, because for us, even we get a batch of SMC, we take 10 tensile tests, we can see a range of 30% just in the tensile. So like,
that's quite common, yeah.
So for us actually designing in that material, we actually, again, we're not probably using anywhere as complex like the Abacus, we're probably using SolidWorks present, but treating the material as an isotropic value. But the problem for us is we have to have big factors of safety in our designs to allow for the anomalies, which
no, that's one of the strengths of firmware, really, is to say that rather than using a big safety, if you're using a big factor of safety, really you're saying the material is not very good, and it's not true. It's just that you're not using the right tools to simulate it, and so there's something, that's sort of what firmware's for, and I can show you some pretty good results actually. That you look at those material tests and you go, well, there's a lot of scatter. If you change the geometry of that coupon, you'll get the same amount of scatter, but somewhere else on your plot. It's really interesting. But firmware can predict all of that, and for different, once you start, because the scatter is geometry dependent, it can predict it for different geometries, what you would sort of expect, and that means you can reduce your factors of safety.
Okay. No, I think it'll be interesting to catch up at some time on that.
Yeah, sure.
Thanks.
Okay, next question on the chat. People are welcome to put their hands up, same as Stephen did, if that's easier. So next question you've had in is, can you simulate permeation and leaking of the H2 pressure vessels?
No, again, we're really involved in the structural side. We've been working with a sealing specialist to develop our own sealing concept that we use that works for us. But at the moment we're doing type 4 anyway, so we have a liner in there to handle the permeation.
Okay, thank you. Next question. Would you consider incorporating structural optimization into your software?
So by this, I guess this is sort of the automated structural optimization tools. So it does some of the work for you. Yeah, it's definitely interesting. I think what we often do is, we sort of split those out, and we use the automated structural optimization tools to give us ideas of the best way to do it, but then tend to use a human to do it, just because I think there's some balance in having a human do it, that they can consider all of the load cases and all of the sort of manufacturing considerations simultaneously for experience, which I don't know if structural optimization tools, in our experience, are as good at doing. So I think definitely we do use structural optimization tools, and they're not interlinked, though. We use them in two different ways. So I guess it's a joined up tool. Yeah, it's definitely worth considering.
Okay, you've got 3 more questions, just so you're aware. Next one is, can you operate the DIC at the same high rate as your dynamic testing? And what is the limit?
Oh, I don't know. I might have to take, if I can find that question and take it away, I can talk to the lab about it. We do image recovery at around 300,000 frames per second for the dynamic. So I guess if you had enough computing power, you could feed all of that into DIC. But I have to check with the lab.
Okay, what we'll do with that is I've made a note of who asked the question, and then we can pass that over to you to talk about offline. Okay, next question. Can the SMC tool also accurately simulate toe-based DFCs?
I don't know what those are, I'm afraid. Does someone want to help? DFC.
Question came from Rizwan. So Rizwan, do you want to just explain that one a bit more?
Yes, hi. Thank you very much, Tim. It was excellent presentation, very informative for me. So I'm talking about, stuff like HexMC, where you've got, so unlike the traditional SMC, they've got significant length and width. So generally, based on hexply, they have created HexMC and other where you've got significant thicknesses of those toe. So is that something that you are, so mostly, prefab based?
Yeah, I think it would work for those. I don't think we've tested it, but I think the way it works would cover HexMC.
The reason I'm asking is that because they're again with those toe-based composites, because we've done a lot of simulations for that, it's highly dependent on how accurately you can represent the architecture, unlike SMC, which is very purely random. Whereas the toe-based ones will also depend on the fiber length and how realistically you can achieve that. So what I'm trying to really ask here is, can you actually account for varying sort of fiber lengths and how that affects the volume fraction that you achieve? Or do you actually have one kind of a common sort of a geometric representation for the SMC in your tool?
Yeah,
So,
it does. I mean, our approach at the moment and where we're going with it does struggle with changing fiber fraction.
right.
So it is really it creates a homogeneous property which is then randomized throughout the structure. So it's not really set up to do that sort of detail. And I guess the benefit of it doing our way is that it's much faster, so you can get results much quicker. Whereas as some of the other ones that look into more detail, the computing times are just much longer.
Yes, yeah, that's definitely the case. In fact, but I think that's something probably we can look at, because the tool that we developed, it works with the Abacus. It's actually much faster than the ones that are already there. We have a paper in Composite Part B last year published that. Maybe you can have a look at that. If you want, I can send you that as well.
Yes, please do. And also Connie, who's on the call, might also be interested in that. Maybe she already knows.
Yeah. Okay. And just while I'm on the chat, so can I just also ask about if you have actually worked on the thermoplastic sides as well? Things like, we have been recently working with Alien, and we were wondering if other people are working on that as well.
I mean, in what respect? We characterize and design with thermoplastics. To us, it's. Do you mean in terms of the SMCs or?
No, in terms of the simulation with the 3D thermoplastics composites.
Oh no, not in like Firma. Firma's very much a sheet. Is for the sheet sort of components. Once you get into the bulk, it does become more difficult. But a lot of those can, you can sort of take Stephen's approach and do it more sort of. You just assume it's a common material, isotropic material for some of them, but it depends on the scale.
Yeah. Okay. Thank you. That's great. I'll try to catch up with you then after the meeting as well. Thank you.
Yeah, it'd be great to talk.
Thank you. Bye.
Okay, and last question, unless there's any other hands raised, which I can't see. Can the crash simulation predict whether a vehicle needs or can be repaired, or if it should be written off?
I mean, the written off question is sort of falls for the insurance company, isn't it? But the crash prediction tool will tell you which bits are broken and to what extent they're broken. It will even tell you what debris left. Now, we've never found a useful application for knowing what debris left, but it's a demonstration that the software knows what's going on. It knows what forces are there. It knows what the material can take in that situation, and so it tells you which bits break, and therefore we need to be replaced. And on the other parts, I mean, it's all connected into Abacus, so it'll tell you things like the max stress on other components. It's very good at working out where the forces are during that crash, where the forces are going, what's absorbing them, what's bending, what's buckling. All your normal failure modes are in there, as well as it's a much more accurate way of modeling the crush, which is the bit that the traditional FEA programs get wrong, but the most important part. And so you can look at all the parts in your simulation. You can see whether they've just completely crushed and shattered and turned to dust, or you can look at parts. What was the max stress that this part saw, for example, or did this bit buckle? So yes, it can tell you that in a predictive way.
Okay, that's great. Well, there's no more questions that have come through to me on chat, and I can't see anyone with their hands raised. So if there's anything else anyone wants to discuss, or if anyone would like to give a brief introduction to who they are if they weren't here at the start of the session, please feel free to do so now.
Hi everyone, sorry I joined a little late. I had another meeting that overran. I'm Chris Worrell, composites consultant at TWI. fantastic presentation. Thank you very much. And I'll be in touch afterwards, Tim. We did meet briefly at the Composites UK Summit in London. I was there as well, so I'll catch up with you later. Thank you.
Yeah, great. It was good to talk, Chris.
Hello, my name is Guo Gongren. I'm working at the University of Hertfordshire. Can you hear me?
Yes.
Good. I was thinking about the SMC, and I assume it's the SMC using the chopped fiber.
Yeah.
We worked on the SMC some time ago, and also worked on natural fiber SMC using the conventional polyester or vinyl resin system. We also worked on a lot on the SMC fire properties, fire retardant SMC, or other materials similar to SMC. I was just wondering if something, I know some people did the simulation on the fire properties. Now probably more important is the thermal properties of the SMC, and which linked to their composition, it can be improved. On the carbon fiber SMC you mentioned, are they fabric, or are they chopped, or I know lots of waste carbon fiber coming into the stream. Not sure which one is the major component of the SMC.
Yeah, what we're looking to simulate is the chopped fibers. That's the one we saw that there's there's an issue in the way that they're simulated, and that we think there's a better way of doing it.
So it's a chopped carbon fiber SMC.
Yeah.
Okay. Are they produced in the UK, or because not many people are making SMC in the UK now, I think.
I couldn't tell you. The partner we've mainly been working with is European, not
Okay.
UK.
Okay.
Okay, if there is any more questions for Tim, or if there's nothing else that anyone wants to raise, then we'll bring this session to an end. I'd just like to say once again, thank you to Tim for presenting today. It was very interesting and seemingly brought up a lot of questions, which is fantastic. So if anyone would like us to connect Tim with anyone, then please let us know, and we can facilitate that as well. So thank you all for attending, and we'll hopefully see you all soon.
Yeah. One second. One question I was just thinking about it. I would like to raise is that the thermal properties and the fire properties of the thermal sets composites, or particularly let's say SMC or DMC, that sort of fast manufacturing process, low cost composites. Now with the carbon fiber added bits of the carbon fiber there, I will assume the raw material cost won't be too high. I was just thinking if I've been reading quite a few papers and things, the thermal property and the fire property could be one thing we can look at it, and we had experience on it, and we thought we can do some contribution on the composition part. I'm just wondering if any of you interested, so we can form a small group, see if we can pursue some of the new materials for thermal properties and for fire properties.
Yeah, happy to talk about it. Maybe it's a separate meeting, and we can talk about it another day. But it's it could be an interesting area. As mentioned, we're sort of mainly looking at the structural side, but it could be that if we can get improved structural properties at temperature compared to other materials, then it could be an interesting one.
Yes. Yes, absolutely. Thank you.
Okay, then I think if we draw that to a close, again, if anyone would like to raise anything after the meeting with Tim or with Composites UK, please let us know, and we'll get that sorted for you. Thank you all very much.
Thanks everyone. Thanks for coming.